Good day, everyone. My partner Raimundo José Muñoz Pons and me, Angel Alcántara González, we will present our project Feature Extraction for Image Classification using genetic programming. In this project, we explore efficient optimization techniques using simplified operators to address the challenge in feature extraction for image classification tasks. And well, feature extraction is one of the most critical steps in image classification. It involves identifying relevant patterns or characteristics from image to improve classification performance. However, there are challenges associated with this process. Manual feature extraction requires domain expertise and can be very time consuming. While deep learning automates feature extraction, it comes with high computational cost. To address this challenge, we use genetic programming or GP as a solution. GP allows us to optimize feature extraction pipelines while reducing the complexity and computational demands. And well, let's talk about the state of the art. Our project is built upon previous work in the field. First, genetic programming has been successfully applied to feature extraction, as demonstrated in the study by B. et in 2020. Second, while deep learning methods achieve high accuracy, as shown by Krzyzewski in 2012, they require significant computational resources, which limit their accessibility. Finally, feature extraction operators like Hawk and LBP, highlighted in Dahl and Triggs in 2005 paper, have proven to be highly effective. However, there are gaps in the research. For example, there has been limited exploration of simplifying GP frameworks that can reduce complexity. Also, few studies focus on constrained tree depths or smaller populations in GP. What data did we use? We use a MNIST dataset, which is a benchmark dataset widely used in image classification. It contains 70,000 grayscale images of handwritten digits, ranging from 0 to 9. Each image has dimension of 28 by 28 pixels, normalized between 0 and 1. Out of these images, say 60,000 images are used for training, while the remaining 10,000 are reserved for testing. These data allow us to efficiently test and evaluate the performance of our feature extraction pipelines. And well, now let's discuss how genetic programming works in our project. GP is inspired by the process of evolution to optimize solutions. It starts with random tree structures where each tree represents a pipeline for feature extraction. We use several operators of the image data, including HOG for histograms oriented gradients, Sobol for edge detection, Gaussian filter for smoothing, and LBP for local binary patterns. The fitness of each tree is evaluated using support vector machine. Trees evolve through genetic operators like mutation, crossover, and selection. This evolutionary process allows us to refine the feature extraction pipelines over multiple generations.
In our implementation, we use a binary tree instead of use a tree without limits or chalice as the article does. This was to avoid higher complexity than our equipment could handle. We also reduced the number of the operators that the tree could select for the nodes. And the last change was the way that we represent the constants of the functions. For example, the standard deviation for the Gaussian filter. Here, instead of represent these constants as terminal nodes, we represent these constants as attributes of the tree class, and we only make sure that we're going to initialize these constants as the same way that the article does. These are the operators that we use for the tree. The first two operators are operators to extract the features from the image, and there is a mistake. I'm sorry for that. The output in those operators, in these operators, mostly vectors instead of image, and the last two operators are operators of concatenation. Also, there is a mistake answer for that in the input in the previous to the last operator in the operator via conit, the input must be to image. That operator was does is concatenate well, flatten the image and concatenate the vectors to return only one vector. And the rest are operators to for filtering and pooling. Um, well, the parameters for the JP algorithm was pod size of 10 individuals, 20 generations, and initialize the population with random trees with a max t of 3. This was released with the method full, so all the trees are gonna be full trees, at least at the beginning of the algorithm. The fitness evaluation function was the function that trained a super vector machine using the future vectors extracted by the trees, and the accuracy is what does function return. For the of the spring, well, or generate the new population in each generation, we use these three operators. The first one is the selection operator, which implement the tournament selection to select an individual from the population. The second one is the crossover operator. This only select two crossover points. Well, one crossover point in each parent, and take the sub-tree for the second parent and replace the crossover point by the sub-tree of the second parent in the first parent. Eh, and the last one is the mutation operator, who only what does is varies all the constants in the class. And the results, well, the best fitness was well, the best model was a model with accuracy of 97.70%. And there was early convergence, to be honest, with the JP algorithm. Because in the first generation, there was the best individual has a fitness of 96%. So only after all the JP algorithm, the increase or improvement only was 1%. 1%. The best tree that we got was this. As you can see in the image, this tree has a depth of 4 because even when we initialize the tree, we only depth of 3. This was because when we make the crossover, we select randomly the points on each parent, and this could result in a tree with a depth higher than 3. In conclusion, well, the only early convergence limit the exploration of the more complex solution. Maybe this could be because the fixed set deep and the small population size and the small number of generations may have constrained the diversity. Uh, and well, at the end, a simplified JP algorithm achieve a high data accuracy in the LMNIS dataset for extract the features to train the SMB model. And this was with a reduced computational effort. I have to say that the genetic programming algorithm takes around 2 4 hours to finish with a population of 10 and 20 generations, and that's the reason because we didn't run more experiments with higher population or generation. And that's gonna be everything for the project. Thank you for your attention.